Hi class, this is the pre-lab lecture video for experiment 1, which will be carried out week of September 11th, Monday, September 11th. There are several parts to this experiment, so please watch this video and listen very carefully. The first part of this experiment is due no later than September 10th. This is the laboratory safety part. Instructions have been emailed to you the week of September 1st on what to do and where to find the lab safety training presentation, where to take the quiz, and where to watch the lab safety video. I have also uploaded these instructions on Moodle under the lab folder under experiment 1. The document is titled Part 1 Laboratory Safety Instructions. You have to receive an 80 on the safety quiz in order to be granted access into the lab, and the deadline is September 10th at 5 p.m. The second part of the experiment, note these are all pre-lab assignments, meaning you have to do them before coming to lab. Part 2 is an MSDS assignment. An MSDS is a material safety data sheet. We have these on every chemical there is. It's extremely important that you familiarize yourself with the sheet. Make sure you complete the MSDS assignment, read everything very carefully. This lab manual is very detailed so that there is no room for misinterpretation. And as always, if something is unclear, please ask me or one of your lab instructors your questions. The material safety data sheets are on page 6 of your lab manual and page 7 of your lab manual. There is a folder on Moodle under experiment 1 with the MSDS sheets that you need in order to successfully fill this out. Make sure you use 2 different chemicals, and as always, write your name on everything that's passed in. So that's the pre-lab assignment, part 1, lab safety, part 2, MSDS assignment, and of course, as with every experiment, part of your pre-lab assignment is to actually read carefully the lab introduction and through the entire lab experiment, as well as watch the pre-lab lecture video and fill out the pre-lab lecture worksheet. With every experiment, your pre-lab lecture worksheet is one of the ways to be granted access to the lab. Your pre-lab lecture worksheet is available under each experimental folder. So for this week, it's under the lab folder on Moodle, under experiment 1. You'll find a Word document labeled Experiment 1 Pre-Lab Lecture Notes Worksheet. You have to fill this worksheet out. You can fill it out electronically if you'd like, or you can fill it out by hand and show your lab instructor. You fill it out in the same way as I am filling it out so that it ensures that you've actually watched this video. So let's go ahead and cover the topics that you will be covering for Lab 1. So Lab 1 deals with really 2 main topics. As I mentioned in the CHEM111 introduction video, you do not need to set up your lab notebook for experiment 1. However, you will have to set it up for all subsequent experiments. Experiment 1, your lab instructor will teach you how to properly set up your lab notebook. In experiment 1, we have really 2 main parts: accuracy and precision, and making observations. These are labeled Part A and Part B in your lab manual. So let's go over first making proper measurements. It's always important to make sure you write the number and the unit down, meaning you can't just write 43. You have to tell me 43 what? Is it 43 grams? Is it 43 milliliters? Is it 43 liters? Is it 43 micrograms? The unit is extremely important. It tells you a lot of information about what you're working with. As some of you may know from high school, when measuring liquids, you must read the bottom of the meniscus. What is a meniscus? If we take a look over here, it's kind of like a contact lens. When you have a contact lens, the bottom, this concave, this is what we call the meniscus. When you read at the bottom of the meniscus, so here we have 40, 41, 42, it's at 43, okay, so 43. But now we have to estimate 1 more digit. We're certain it's at 43, but the bottom of the meniscus, someone might read 43.1, someone might read 43.0, someone else might read 43.2. So you always estimate 1 digit beyond the last marked on your measuring device. This gives you what we call proper significant figures. Make sure you read your textbook before coming to class on Friday and before your lab experiment. It goes over carefully what significant figures are, and we will also go over it in lecture. So as I mentioned, you want to write down your number and estimate one digit beyond. Here I see this as 43.1, and your units. This is a graduated cylinder. We're measuring liquids, therefore my unit is ml. So 43, I'm certain of 43. The 0.1, this is my estimated digit, and milliliters, this is my units. So this is how you should always record any measurements taken. On balances in lab, you have to record all digits shown. Meaning if your lab manual says, for example, weigh 1.2 grams of copper chloride, your balance is actually going to show beyond this 1.2. So your balance, for example, might show 1.204 grams. This is the number that you write down. You don't write 1.2, no balance or balances that are used in our chemistry lab read beyond 1.2, so you have to write down all the digits shown in your balance. Let's go over more examples on how to write down measurements, how many digits to estimate based on the measuring device that you have. So let's take a look at ruler 1. We're going to measure the length of the shark. So we have increments, 10 increments. So here I'm certain that it's between 5 and 6. So therefore the number that I'm certain of is 5. Certain for ruler 1. Now this looks like it's slightly beyond 5.5. So someone could see this as 5.6. Someone else could see it as 5.7, 5.8. The estimated digit is where the uncertainty lies. So I'm going to say this to me looks like 5.7. So 5.7 is my estimated digit, and my units are centimeters because it tells me here what my units are. Every measuring device will have the units on them. Now let's take a look at this ruler. Notice how the increments are actually a little bit more precise, more graduated. So again, the shark tail is beyond 5, so I'm sure of 5. There are actually increments here, which also gives me some certainty. So here I have 5.1, 5.2, 5.3, 5.4, 5.5, 5.6. This dotted line is right on 5.6. Now, is it exactly on 5.6 or is it slightly over 5.6? This is where, so these two numbers I'm absolutely certain of because of these graduation marks. I see it as 5.61. So this is where my estimated digit is. Now am I done? I'm not done because I have to write my units. So make sure you go over this very carefully. Writing proper measurements is extremely important in a chemistry lab because if you're making measurements and you don't know the units that you wrote down, you could actually result in a very unsafe place to work in. So part A is the search for the best volume measuring device. So this is what we call accuracy and precision. It's really important to understand this concept in a chemistry lab. Your lab instructor will tell you which device is actually best to work with in terms of measuring volume. So this is what we're going to be working with today. We're going to be measuring volumes. So just to kind of review, accuracy, think of these words as you would use them in everyday life. It refers to the proximity of a measurement to the true value of a quantity. Precision refers to the proximity of several measurements to each other. So in part A, we're going to be comparing 4 measuring devices, and we're going to compare their accuracy and precision by measuring 10 milliliters of distilled water. Now, we're going to be measuring 10, so an example of the data that you might be collecting, so why are we using water? Just to backtrack a little bit, water has a density of 1.00 grams per liter, meaning theoretically, if you measure 1.00 grams, this should equal to 1.00 milliliters. So what you're doing in lab is you're going to measure 10 milliliters of water using each of the measuring devices below and determine their mass. So you're going to use a 10 milliliter volumetric pipette, you're going to measure out 10 milliliters of water, and then you're going to weigh it out. You're going to do this several times according to what your lab manual says. Your lab manual actually says to just measure it 3 different times. So each time you're going to measure out 10 milliliters of water using a volumetric measuring device. So whether it's a volumetric pipette, a graduated cylinder, a beaker, or 25 milliliter Erlenmeyer flask, and then you're going to weigh them out. So if we take a look at the 10 milliliter graduated cylinder, we measured out 10 milliliters as closely as possible of water, and then we weighed it out into a tiered beaker and figured out its mass. Similarly with our 50 milliliter beaker, similarly with our 25 Erlenmeyer flask. So we can take the averages here. So if we wanted to calculate the average, on page 11 of your lab manual here, I have an example on how to actually calculate average. So the calculation of an average is the sum of values over the sum of numbers of measurements. So here I took 4 measurements, therefore I add these up and I divide by 4. And I find, if I do that, I find that my average for the volumetric pipette is 99.9 grams. Again, I add these 4 up, I divide by 4 because 4 is the number of measurements, 9.84 grams. Again, for my 50 milliliter beaker, 9.59 grams. And lastly, 8.38 grams. My true value, so I'm trying to figure out the one that's most accurate and most precise. My true value, I'm trying to find which device will give me closest to 10 milliliters. This is my true value. This is what I was discussing with you up here. 9.99, 9.84, 9.59, and 8.38. Therefore, according to my data, the 10 milliliter volumetric pipette is very close to the true value of 10.0 milliliters. So in conclusion, what conclusion am I drawing here, which is expected for you for part A? You want to tell me which device is most accurate and which is the least accurate and precise. So to me, based on the data set here, these individual data points, and based on the true value, it looks like the 10 milliliter volumetric pipette is most accurate, and the reason I concluded this is because it's the closest to true value, and the true value was 10 milliliters. Here I have 9.99 grams, and again, because of the density of water, 9.99 grams is in fact 9.99 milliliters. It's also the most precise because all the values are close to each other. All the values are close to each other. One way to determine precision is to calculate something that's referred to as mean deviation. Mean deviation sample calculation is available to you on page 11 of your laboratory notebook. So calculation of mean deviation is the sum of deviations from average divided by the number of measurements. So the deviation from average, you calculate it by subtracting the measured value from the average value. And of course you ignore the sign. So let's do a sample calculation here. Let's first define it. Mean deviation is equal to the sum of deviations from average over number of measurements. The smaller this number, the better the precision. So keep this in mind. Now, based on this, what do you think the least accurate and least measuring device is? Well, it looks like actually the Erlenmeyer flask is the least accurate. It's the farthest away from true value, and it's the least precise. It varies, it fluctuates from 7.5 to 9.0. So we would never want to use a 25 milliliter Erlenmeyer flask to measure any volume. Based on our data here, it looks like the 10 milliliter volumetric pipette is in fact the most accurate and precise measurement. Now, in part B of your laboratory experiment, so that's part A, kind of learning how to actually record data, understanding density, and also familiarizing yourself with different measuring devices and understanding firsthand accuracy and precision. Part B of the lab experiment involves making observations. So there's a difference, of course, between observations and interpretations. Make sure you read your lab introduction very carefully to go over this. The key here is we really have two types of observations in a chemistry lab. The first type is what we call a quantitative observation, quantitative, quantity, and qualitative observation. So if you take a note here, this observation, or description involves making measurements. So qualitative observations are ones that involve making measurements. If you note, we have the root word quantity. So kind of to make it easy for you to remember, quantitative observations requires numbers. Okay, so an example of quantitative observation that you would have to make, for example, 5.0 milliliters of X solution. So whatever solution is that you're working with. It doesn't have to be a solution, it could be grams. You're actually working with a solid in part B of experiment 1, so you're actually going to be writing the amount of solid weighed, actual amount that is displayed on your balance, and the name of what you weighed. Qualitative observations is a description without, so it's an observation or description without measurement. If you notice, it comes from the root word quality, meaning it's describing the quality of something. It does not require numbers. So let's do an example together. So if I have a solution, I want to describe the solution. So I'm going to describe the solution in a qualitative fashion. So I'm describing what it looks like to me, maybe what it feels like. Is it very fluid? Is it more viscous, etc.? So for example, a solution can be described as pale yellow. So I don't want to just say yellow because there are different spectrums of yellow. And I can say it's actually a pale yellow transparent solution. So when someone reads your lab notebook and they go into lab, they actually know what you're referring to. So that's how detailed your observations should be. In part B, you're going to be making observations based on a chemical reaction that's happening. Part B, you're going to actually be performing quantitative observations and qualitative observations throughout the steps here of the experiment. Make sure you answer any concluding questions for part B, and if there's any for part A. For ease of data, making data observations, I've kind of set an example of what tables should look like for you in part A of your lab notebook. And again, just to emphasize, I actually have a sample calculation for you here on page 11 of your lab notebook. Now just a few experimental logistics for you for experiment 1. Make sure as soon as you go into lab, either show your instructor or your TA, your lab instructor will communicate this to you very carefully, your pre-lab lecture worksheet. So this worksheet here, you have to have it filled out to be granted entry into lab. Otherwise, you'll receive an undropped 0. Make sure you pass in your MSDS assignments. They should be 2 different assignments, 2 different chemicals. And then for part A, you're going to be working in groups of 4. All of this is specified in your lab manual. Part B, you can work in groups of 2. If you choose to work alone, that's fine. Part E, you're going to be practicing making observations, qualitative and quantitative observations of a chemical reaction. You're going to practice outlining observations and data in your lab notebook and practice recording observations and data in your lab notebook. After the experiment is complete your data analysis questions, turn in your lab notebook pages and MSDS worksheets, and then take a brief, short post-lab quiz that is passed in lab as well. Once you're done with that, you can then go home, but of course, before you take your pre-lab quiz, make sure your lab station is clean. We have very many students actually going through our labs this semester, so we want to be respectful of everyone's space. As always, email me any questions that you may have.